Okay, let's go ahead and get started. I'm Charlie Smith, the Executive Director of ESIG. It's nice to see everyone here at the end of the week of the IEEE PES meeting, and welcome to our ESIG monthly webinar for July. Just be glad you're not down in steamy Orlando. It's pretty hot down there. For those of you not familiar with ESIG, we're a membership-based nonprofit organization providing our members with objective information, resources, and networking opportunities in support of the energy transition. We do this through workshops, tutorials, webinars, blogs, working group and task force activities, and producing technical resource materials. I also serve in a leadership role with the Global Power System Transformation Consortium, the GPST, whose mission it is to bring together key actors to catalyze a rapid, clean energy transition at unprecedented scope and speed. ESIG leads Pillar 1 of the 5 pillars, which deals with the research agenda for the system operators. We just finished 2 of our more topical workshops in Denver in June, one on forecasting and markets, and the other on long-term load forecasting under an accelerating time frame for DER applications and electrification of load. Never a dull moment, and now we're deep into the planning for the fall workshop in San Diego at the end of October. I can assure you we will have another great lineup of tutorials and technical sessions, and I hope to see you there. Further information can be found on our website, and the final agenda will be posted in a couple of weeks. Our workshops and monthly webinars are open to everyone, so please feel free to register anytime on the ESIG website. If you're new to ESIG, I strongly encourage you to follow up with us if you like what you hear, and I think you'll be pleasantly surprised. ESIG membership will give you an opportunity to participate actively in all of our working groups and task forces. You can find us on the web at esig.energy, as well as on LinkedIn, Facebook, Twitter, and YouTube. Okay, just a few logistical matters before we get started. First of all, phones will be muted for the duration of the webinar to avoid unnecessary distractions. For the Q&A, we're using the Slido platform. So to ask your questions, please go to slido.com and enter ESIG20 as the event code. The instructions are also at the bottom of the screen. You'll see a thumbs up button next to the questions to allow you to cast a vote to help prioritize the questions submitted. We plan to save 10 minutes or so for Q&A at the end and then wrap it up at the top of the hour. An email with a link will be provided once the video file has been posted. We also plan to provide short responses to unanswered questions after the webinar, so please don't be afraid to ask your questions through Slido. Okay, today's topic is going to be on the evolution of protection schemes for a system with a high share of IBR. This is a topic of ever-increasing interest and importance as we transition to a power system based on IBRs with very different short-circuit current characteristics from conventional synchronous machines. And here to talk with us about it today is Steve Sano of the Hawaiian Electric Company, where he has 31 years of experience, with the last 13 years as manager of the protection department. HECO is a longtime member of ESIG, in fact, one of the 6 originals going back to 1989. HECO is in the middle of an unprecedented energy system transformation on the way to a 100% clean energy system by 2045, dominated by IBRs, coming from a system dominated by imported fossil fuels only a decade ago. HECO is a valued member of ESIG, and it's my great pleasure to welcome Steve here today. Today's webinar will address Hawaiian Electric's protection roadmap, which looks at the possible changes that will be needed to the grid's electrical protection systems in response to the increasing levels of IBRs at all levels of the system. Historically, protection systems have been based on a strong grid consisting of centralized, transmission-level, rotating synchronous generators. Our future protection system will have to deal with some things we know about, like distributed generation, shorter critical fault clearing times, lower fault currents, and uncertain directional relay performance, and some things we don't yet know about. I greatly value the contributions of HECO to ESIG and the industry, and I look forward to what Steve has to say. Just a short reminder once again to use Slido at slido.com with the event code of ESIG20 to ask your questions. Okay, without any further ado, let's go ahead and get started. Steve, I will now turn it over to you.
Okay, thank you, Charlie. Let me get my screen shared. Okay, can you see my screen?
Yep, we see it. Looks good.
Okay, very good. All right. Good morning, good afternoon, or good evening, everyone, depending on where you're at. Again, my name is Steven Sano. I'm the manager of the protection department over at Hawaiian Electric, and by popular demand, we'll be going over our protection roadmap that we see for the future. Um, what we'll do is we'll go over these things on the agenda here. We'll talk a little bit about the company's carbon emission goals, review some protection objectives, and take a look at some of our existing protection schemes over at Hawaiian Electric. That will lead us into a discussion of upcoming challenges, some of the limitations of our existing protection schemes, and a discussion of what the future protection systems at Hawaiian Electric could possibly look like. And then we'll end with a discussion of the difficulty level of these future transitions that we're seeing, kind of discuss what we think are the time frames on when protection needs to change, and also a short discussion on what might accelerate or slow the need for these changes. So with that, Hawaiian Electric, like probably a lot of your companies and a lot of other industries, is decarbonizing for obvious reasons. Any of you who are suffering through the current heat waves uh, know that there is a need for this. Here in Hawaii, we just had our first tropical storm of the season. Fortunately, the good Lord pushed it south from us, so we had minimal impacts. But we are decarbonizing. And so to do this, our system is changing drastically from traditional rotating synchronous generation, which was fossil fueled, to a future where it's going to be dominated by inverter-based generation. And the protection systems that we have today, which were based on our previous system designs, will need to change to accommodate the future. Now, protection objectives are pretty much what everyone has on their systems. We want to identify and remove faults. We want to minimize the duration and extent of outages. And we want to prevent system instability and, of course, provide for public safety. So these objectives are what we had in the past and what we need in the future. So this is a really quick summary of the existing protection elements that we have at Hawaiian Electric Company. And again, this is specific to our systems. You may or may not have the same at your systems. And so we'll try and note that where we can. For our transmission systems, our transmission lines, uh, we have high-speed communication-based protection. Historically, it has been permissive overreaching transfer trip. Um, for the longest time, this has served us well. We do have some limited line current differential protection, and that's becoming more important as we'll discuss a little later. Phase distance, also on transmission, has served us well. We have directional and non-directional phase and ground overcurrent everywhere in our system. Bus differential is mostly at our transmission substations. Transformer differential and overcurrent on our transformers. We do have breaker failure protection at all of our transmission substations and other critical areas. Our circuit breakers operate in 3 to 5 cycles. depending on where you are, if you're on transmission or distribution. We do have circuit switchers, which were installed more for the physical space considerations than for speed. Um, Fuses are everywhere on our system, and we do have, sadly, a fair amount of electromechanical relays still on our system. We've made great progress in converting to digital relays, but those electromechanical relays are still there. Okay, so that's our protection systems based on the past, how our system evolved through our rotating synchronous generation on our transmission and then down to our distribution. These are the challenges that we are currently seeing with the shift to inverter-based generation. There are knowns and possibly unknowns as to how inverter-based generation will affect our existing protection schemes. And there's always the concern that it may misoperate. Our protection schemes could misoperate. So some known challenges, available fault currents are decreasing. Inverter-based generation does not have the same short circuit performance as rotating synchronous machines, and fault currents are decreasing. Our systems are getting weaker, meaning that our critical clearing times for transmission faults are getting lower. We have to clear faults faster. Inverters themselves can drop out faster than our relays can clear faults. Many evolving standards for inverters. For those of you following 1547 and the other transmission standard that escapes my mind at the moment, but our standards are constantly evolving. Inverters can affect relay directionality. This is a real concern for anyone in the protection field. And then the practicality of upgrading old protection schemes. Just very challenging to change some of the old stuff that we have. So that's sort of the known challenges. Unknown challenges, how inverters will react or what their output will be under certain situations. We're finding that we have relay and inverter model for our simulations that are constantly evolving. So we try to take a look at the things that are critical, but we do not know if we are covering everything that needs to be looked at. Inverter simulations versus actual performance. Again, for inverter models, we're getting into highly detailed EMT type models like PSCAD. We think we are capturing their actual performance, but we just don't know. And of course, not knowing what we don't know as we move forward. This is really a brave new world that we're going into here. This next slide I borrowed from EFRI because it is a very good slide. When we talk about weak grids, I think a lot of times people have this false conception that we're just talking about lower fault currents. That is part of the picture, but not a complete picture there. We do have lower fault currents. They behave differently, which is an issue. We do have impacts to voltage, so high DVDI type characteristics. We have impacts to frequency where there is high DFDT characteristics. And you'll see on this particular slide mention of GFM, grid forming inverters. Grid forming inverters look like they have a very good potential to address some of the issues that we're seeing, but we'll talk about that a little bit later. So some of the limitations of our existing protection at Hawaiian Electric. Our POTT schemes I mentioned have served us well in the past, but they can misoperate with inverter-based generation in certain situations because of, again, fault current magnitude and just fault current behaving badly in terms of directionality. Line current differential protection seems to be fairly robust. High speed protection, we're not sure if it's fast enough for certain situations in the future with inverter-based generation. Phase distance can misoperate again because of the directionality issue with inverter-based generation. Directional, non-directional phase ground overcurrent. Traditionally, did not have to be fast. It can misoperate on directionality and increasingly harder to coordinate. As our fault currents start going down, things are taking longer. We're trying to speed things up and hard to coordinate things. Bus differential. At Hawaiian Electric, we have this ancient linear coupler scheme that could misoperate due to inverters. This is more of a homegrown issue. It's just us. Transformer protection in terms of differential and overcurrent protection. Overcurrent, again, slow, could misoperate on directionality. Differential protection, the differential part we think is fairly robust and secure. Breaker failure. So for critical areas of our system, we have dual redundant protection, but the one component that we cannot have redundancy on is the circuit breakers. And so we only have one, and we have to have breaker failure protection. This means it adds another level of protection, which is slower, and it may be too slow in certain situations. Our circuit breakers, again, 3 to 5 cycle circuit breakers, adequate for our system in the past and today, but may not be in the future. I know a lot of you folks have moved on to 2 cycle circuit breakers. We don't have that yet. Circuit switchers, sort of the same situation. They were not installed for speed, but we might need them to be faster in the future. Fuses are sort of a interesting case of our protection elements. You know, they are slow, they are not adjustable, not adaptable. They have served us well, but with the change in our system characteristics, lots of issues with fuses. Electromechanical relays, again, sort of just us here, you know, lack of any sort of event reporting for post-analysis. They work, but they have their challenges. All right. So moving on to possible future for our protection system here. POTT, we are already replacing our POTT with line current differential because of the issues that we've seen with their misoperations. Line current differential, again, pretty robust. The only consideration there is the speed of operation. There's probably going to be a need to move to a traveling wave type scheme for faster detection. Some of you folks may be deploying traveling wave as we speak. Phase distance, again, because of the directional issue and the current magnitude issue, we think might have to be replaced more with overcurrent communication-based blocking schemes. Directional, non-directional phase ground overcurrent. Again, with the decrease in fault overcurrent levels. We believe that overcurrent schemes can still work, but they'll have to be supplemented with communication, which we don't currently have, adaptive type tripping schemes, and undervoltage supervision. So, we believe they can work, but they will require supplemental elements to be added to them. Bus differential, again, it's those linear couplers, and that's just us. Transformer differential and overcurrent type protection. Again, same sort of thing for the differential protection should work. Some issues with the overcurrent and directional, so maybe some blocking schemes for that. Breaker failure. Breaker failure, again, I think I mentioned adds additional time, which we may not have because critical clearing times are getting shorter. We may have to forego breaker failure or overtrip, have primary and secondary breakers, add a second breaker, make it redundant. 3 to 5 cycle breakers, again, if speed is going to be an issue, we'll have to go faster, convert to 2 cycle breakers. Circuit switchers, again, same issue there, speed of operation. So you can get them pretty fast nowadays, so possibly change to faster circuit switchers. Fuses, I mentioned fuses that are everywhere on our system. What do you do about them? Well, we do have programs to replace them with smart fuses, essentially electronic-based fault interrupting devices. Much more expensive than your common fuse, but much more flexible as well. So, fuses are everywhere in our system. It is the most predominant protective device that we have. Would we ever change all of them out? Probably not, but we have to strategically deploy smart fuses as we go along. Electromechanical relays, of course, continue changing those out with microprocessor relays. And sort of along that same vein, replacing microprocessor relays with the next generation. We still have some first generation microprocessor relays on our system back from the 90s. Okay, so that's sort of what the future for our protection systems look like. Changes that will have to be done to accommodate our decarbonization and change to inverter-based generation. These next couple of slides are just illustrations of what these changes could look like. This simple diagram is meant to show a transmission line, the 2 breakers on the end of the line, and the 2 relays connecting them. As I mentioned, we have our POTT is our standard, which we're slowly changing out. So POTT, if it becomes insufficient, we'll change that out to current differential by changing out the relays and possibly the communication. If current differential is not sufficient, we'll have to go to traveling wave. Again, changing out the relays. Hopefully we changed out the COM adequately, and might have to change out the time source. Phase distance, that little diagram that you see at the bottom, showing our stepped zones there, might have to be replaced with things like directional overcurrent with communication, so supervised schemes requiring communication. Again, if things need to go faster, 3-cycle breakers get replaced with 2-cycle breakers. And if things have to go faster yet, we have to forego the breaker failure schemes and put in another breaker, which of course is always a challenge to do. And taking a look at distribution, our distribution circuits for the most part are just radial distribution circuits, fairly simple. Fuses everywhere on our distribution circuits. We do have a fairly good penetration of DER on our distribution circuits, mostly photovoltaic, no battery storage that is out there. As our distribution circuits change with more and more inverter-based generation, we think we'll have to change out things like fuses. So in this diagram, you see the fuses replaced with circuit breakers or reclosers, other devices, and communication everywhere. We need communication to the protective devices, and also to and from the generation sources that we'll possibly have on our circuits here. So again, distribution, although for the most part radial, does need significant changes. All right, I kind of mentioned this a little bit. We've talked about these transitions that have to be done on our protection systems. What we try to do is take a look at these transitions and sort of subjectively classify the difficulty of making these transitions. And again, this is just based on our systems and our experience. It could vary with other places. So POTT, going to current differential protection, our difficulty assessment is a 2 on a scale of 1 to 5, where 5 is the most difficult. So not too bad. Line current differential to traveling wave, again, we think the difficulty is about a 2. Space distance to communication-based blocking schemes, because we probably don't have communication for some of these locations, it's a 3. A little bit more difficult. Supervised overcurrent with communication, adaptive schemes, voltage, that sort of thing. And then sort of a 3 as well. Bus differential protection changes, getting rid of those linear couplers, which we have been desperately trying to do. That's up at a 4, just because of our station designs and the criticality of those buses. Sort of an existing situation that we'll have going into the future. Transformer current differential and overcurrent protection, blocking schemes for the overcurrent. Again, it's sort of localized to the transformer, so not that difficult. It's down at a 1 there. Breaker failure. Foregoing breaker failure, putting in a secondary breaker, that's a 5. That's going to be the most difficult thing for us, primarily because of space restrictions in our substations. We just don't have space for another breaker. Going to faster breakers, from 3 to 2 cycle breakers. Cost involved in that, space involved in that. That's at a 4. Sort of the same situation for circuit switchers. Out at a 4 to get faster circuit switchers. Fuses to smart fuses. We have been doing a bit of this work on our distribution circuits on all our systems. So that's at a 2. We kind of have a better idea of doing that. Primarily a cost issue with that. Again, fuses, traditional fuses, very cheap, but smart fuses, because they're electronic devices, more costly, need more maintenance, that sort of thing. Electromagnetic relay replacements with microprocessor relays. We've been doing that. We just need to keep on doing that to get the electromechanical relays off and keep the current microprocessor relays up to date. So difficulty, we gave it a 2. And again, this is really just our subjective subjective rating of the difficulty. It could be different at different companies and different locations. Okay, this next slide takes a look at what we think will trigger the change for these protection schemes. Things like POTT, our current high-speed transmission line protection scheme, we're already seeing issues, so that's being changed out with phased out rather to current differential. Whenever we put in a new IBR-based generation plant, lines around the plant are converted to current differential if they are not already current differential. Current differential for transmission lines, again, it's a speed issue. We think current differential itself is fairly robust, fairly reliable, but the speed may not be sufficient, so we might have to change that out to traveling wave. And again, it's the critical clearing time not being met by existing line current differential. Phase distance, again, it's the unreliability of that scheme with inverter-based generation near to it. Phase and ground overcurrent, when the max load and min fault levels are starting to encroach, we don't have sufficient margin to maintain secure operation. We need to start looking at changing that with other supervision schemes. Again, our bus differential situation with the linear couplers, we just need to get those out as fast as we can. Transformer differential and overcurrent, again, the overcurrent part, the need to add supervision on overcurrent. Breaker failure being driven by critical clearing times again. When is it going to be too slow? That is a concern for us. Changing circuit breakers to faster circuit breakers, again, it's a critical clearing time issue. Not being fast enough. Circuit switchers, same thing, critical clearing times. Fuses, when they get too slow or don't operate for a lack of fault current, miscoordination. We're also changing fuses out for reliability, so there are other opportunities and triggers for fuses. But again, it's primarily the decrease in fault current levels that are causing that. Electromechanical relays, again, it's an ongoing process with that. If anything, we just have to keep going and maybe go faster on that. So, we sort of have identified the changes that we see for the protection systems. We have talked about some of the triggers we see for these changes. And of course, the question that everyone wants answered is, when will we reach these trigger points for these changes? And unfortunately, we don't have a crystal ball that will tell us this. Certain things, we're seeing now, and others we're keeping an eye on. Things like POTT, we have seen issues currently, so that's being done now. Changing line current differential to traveling wave. We haven't seen anything on our system that would indicate we need to change that. And again, it's a critical clearing time not being met by current differential schemes. Phase distance, fault direction unreliability. We see some of that already, so there are changes being made. Phase ground overcurrent, when max load and min fault levels are getting too close to each other. We haven't really seen that, but we're keeping a close eye on that. Bus current, bus differential, linear couplers. um, our homegrown problem that's being addressed now. Transformer differential and overcurrent, sort of the same as the overcurrent issue, keeping an eye out for that. The next three over here, breaker failure, going to faster circuit breakers, faster circuit switchers, again, all driven by critical clearing times for that. Fuses, fuses being too slow or not operating, but we have other opportunities to change out our fuses as well. Microprocessor relays, we have a process for that now, and again, just needs to be ongoing on that. So again, no crystal ball that will tell us, when we need to do all of these things. Predicting when these trigger points will occur, this next slide sort of summarizes what our current thinking is on this. Timing is currently unknown, very difficult to predict, and highly variable. Detailed, accurate simulation models are needed to forecast upcoming changes to fault current levels, critical clearing times, how fault currents look, if the relays can see what's going on adequately. Our simulation models are getting better. I want to say there are certain areas where they're lacking, but progress is being made. If you don't have good models, we need to monitor and investigate field readings and events. We need to track changes and be able to extrapolate when these trigger points would occur. We need to implement automated systems to be able to track changing trends on our system. And industry standards and guidelines. So, to the extent that we have best practices and protection to address some of these things, we can make those changes now before we meet our trigger points for some of these things, head them off, so to speak. And lastly, different system resource types at different locations may accelerate or delay the need to replace some of our protection systems. The main takeaways from this slide is that really the timing is unknown, difficult to predict, and highly variable. And the last bullet point, different system resource types at different locations may accelerate or delay the need to replace protection. So this next slide here sort of tries to summarize the resource impacts that we think we'll be seeing over here. So again, depending on what the resource is being added, what type of resource is being added, it has a different impact to relay and protection system performance. If you add synchronous generators to the system, our system, there's really no impact. Our system was designed to accommodate synchronous generators. But if instead we add things like synchronous condensers, which are similar to synchronous generators, the impact to relay operation minimal. So again, on this subjective rating scale, we have 0 to 5, with 5 being the worst. Synchronous condensers are about a 1. Static VAR compensators, StatComs, again, sort of a similar thing. Impact would be a 1. Grid forming inverters versus grid following inverters. This is sort of a very interesting area that is evolving on our system. Current indications are that grid forming inverters will address, to a certain extent, the issues that we're seeing with the weak grid issues. So grid forming inverters, because they offer more flexibility, more capability in terms of fault current behavior in terms of voltage support and frequency support. Grid forming inverters, we think, will range from 0 to 3 on the impact to our protection systems. As compared to grid following inverters, which we believe is like a 4 to a 5 in terms of the impact to our protection systems. Again, just because of the differences in the operation of grid following versus grid forming. Controlled DER. So DER that's out there that we have control over. That's rated at a 4. Uncontrolled DER, but with future ride-through settings. We've rated that as a 4. The ride-through settings that are sort of evolving are giving us a better confidence in the protection system performance in certain situations, both at local and system levels. So that's up at a 4. Uncontrolled DER, which is sort of our default current environment, just because of when all of our DER went in on our distribution circuits. Uncontrolled, we have no visibility on it. It's at a 5. So that's sort of what we see in terms of the resource impact to the changes to protection system performance and how things are going to evolve. And with that, that is the end of my presentation. So we can address any questions that have popped up.
Okay, thanks for that, Steve. Before we jump into the specific questions, and there's about 20 of them, and a lot of them are from the point of view of practitioners. So I think there's probably a mix of people on the line. So sometimes it might be good to give a little bit of background around the question. I'm not a protection person myself, but I know that there are a lot from the questions that we have. But could you give us a little bit of a sense, Steve, for where you think HECO sits in the spectrum of companies that are on the journey from a traditional synchronous machine-based system to a very high IBR system? You see yourselves as kind of early in the journey, middle of the journey, later in the journey, and how do your problems and what you're seeing with the relaying and protection system compare to what other people are seeing, or what you and your colleagues talk about when you're looking around out there?
Yeah, so I think we are sort of in the middle right now. There was a lot of concern early on because we seem to have a relatively high penetration of inverter-based resources on our system. So a lot of early concerns, but we really haven't seen as significant issues as we thought we would. Again, you're always fearing the uncertainty of the future. So it hasn't been as bad as we initially thought from the protection side in terms of impact to protection systems. So I would say we're kind of in the middle right now.
Okay. And one other general sort of question before we jump into the detailed questions, and that's your perception of the problems on the transmission system with transmission connected IBRs versus problems with protection on the distribution system with the DERs. How do you kind of see the challenges from those two parts of the system compared to one another?
Oh, very interesting. This is a evolving area for us. Before, the transmission system and distribution system were sort of considered separate and not really impacting each other. But now we're seeing that distribution system issues are sort of bubbling up to the transmission system level. Not so much in terms of protection, but in terms of their interaction, things like critical clearing times. We've always had that on transmission. We never had that on distribution, but it seems to be moving towards the case that, we might have to clear faults faster on distribution to prevent impacts on transmission.
So sort of changing, shift in emphasis.
Yes, yeah, a change in perspective there.
Yeah. Okay, let's go into some of the Slido questions here. We've got a number of them. So the first one is the future protection schemes all seem to be communications based. What
Yes.
backup protection is being implemented for loss of communications?
That's actually a excellent question. So, protection systems are going to be dependent on communication. Communication has to work. So, right now, the plan for communication on our systems is we're moving towards this MPLS-based communication system for transmission and private LTE, private cellular for distribution. Our telecom folks are designing in the required level of redundancy for these communication systems. Protection will be dependent on communication in the future that we see.
Okay. The next question is actually a set of two questions, two coupled questions here. So the first looks like a comment. Line current differential or directional comparison schemes with weak in-feed logic will work if there is strong enough IBR fault current. And the second part of that is, when the grid becomes dominated by IBRs, these methods will face problems. How will this affect the methodology, as this seems like a solution for now?
I think I agree with that first point that was made. All of these protection schemes that we have are constantly evolving in this environment that we're in. So although what I've shown is our current thinking on the changes, it's going to evolve over time as we get a better idea from not only modeling and simulations, but actual experience. I think our thinking on the changes are going to change in the future. So yeah, by no means is what I've shown cast in concrete or anything like that. Subject to change, work in progress.
Yeah, may not be the final answer.
Yes.
Okay. What are some of the issues you're seeing with POTT? Distance elements misoperating or weak in-feed or something else?
Yeah, distance element misoperation primarily because of the bad behavior of inverter-based fault current. And this gets back to how the current is in relation to the voltage for non-grid forming type inverters. We've seen it all over the place. The angle swings wildly, so you get incorrect directionality coming out of the relay because of that. The fault is in front, but directionality indicates it's in back, and vice versa, sort of thing.
So
So I don't know if that answers the question or not, but the directionality is a real concern.
okay. There's a related question that I'll throw in there, just since you mentioned that the grid forming inverters have better behavior, better characteristics than the grid following. Is there any move in HECO towards specifying grid forming in the future for your inverter-based resources, or is that a step that you haven't really contemplated yet?
No, we are requiring grid forming inverters for all our future procurements for system resources um, on transmission and to a certain extent on distribution as well, I believe. So uh, there are a lot of benefits for grid forming inverters. Our current thinking is that they will address a lot of the problems we're seeing. So it's actively in the procurement process. We are specifying grid forming inverters.
Interesting. Okay. Um, Next question. Communication schemes can solve IBR protection issues, but installing fiber is expensive. Can you describe HECO's communication system and the challenges and costs with upgrading? I think maybe you touched on it in an earlier question, but this is more related specifically to installing fiber.
Yeah, as protection engineers, we like fiber, right? Direct fiber is the best thing, but very difficult to install that nowadays. So um, direct fiber is sort of being replaced with MPLS, at least on our systems. The MPLS system being planned out um, has the robustness um, to replace direct fiber, and in certain respects, our telecom folks are telling us it has additional flexibility, additional benefits. So we still like direct fiber, but yeah, the difficulties with that have always been a challenge, and these newer systems like MPLS are supposedly as good as direct fiber.
Okay. Question here on what simulation modeling software are you using?
Well, for protection, we are primarily a Aspen one-liner user at Hawaiian Electric for short circuit type analysis. Um, the models in Aspen one-liner for inverter-based resources are constantly evolving. They are getting better. Aside from that, our transmission planning, distribution planning people use PSSE for load flow and dynamic simulations. Um, those models as well are getting better for inverter-based resources, but right now there is no other way to get better information on inverter-based resources aside from EMT type um, software simulations. So things like PSCAD, EMTP type programs, which we currently are using. PSCAD is sort of being the de facto standard, I think, if you want the truly accurate representation of the inverter-based resource behavior.
Okay. Um, how do you plan to overcome the gaps in traveling wave protection if replacing line differential relays with traveling wave relays?
So, traveling wave relays, uh, again, the speed is what we'd be looking for. We can't make critical clearing times with current differential and the current circuit breakers. So, traveling wave will offer, sub-cycle um, detection performance. Um, but if you're still operating a 3-cycle breaker, that may not get you much. So a combination of traveling wave and faster circuit breakers is kind of what we're seeing for the future. Maybe just depends on the critical clearing times that we need to meet with the protection systems.
Okay. Um, Here's one about the future. How will fault ride-through mechanisms for grid forming inverters impact the future protection scheme?
So We think that the fault ride-through um, will benefit the protection schemes in terms of keeping the voltage and frequency up. Those are, the two common areas where we see the critical clearing times being effective. If the inverter-based resources don't have ride-through, they cannot support voltage, they cannot support frequency, the protection systems need that time to, detect and clear the fault. Um, so on one hand, the lower fault currents is causing us to go slower, but then the critical clearing times are requiring us to go faster. So grid forming inverters, by being able to support voltage and frequency, um, hopefully will better enable the protection systems to work by giving them more time, essentially not having the critical clearing times be so short.
Okay, sounds like you've given that some thought. Here's a little higher level question. Does HECO have any plans for ADMS and DERMS deployment? If so, what is the timeline?
Yes, we do have plans. I am not sure of the timeline. Um, those types of systems, to the extent that they offer us visibility and control, down at the distribution level for smaller systems, could be a valuable part of, the overall transition to higher IBR resources in the future. Sorry, I'm not aware of the timeline for that.
Okay. Here's one. I don't know if you'll have heard about this or not, but we'll ask. Have you ever used or heard of substations that apply secondary bus differential relays? Is that protection scheme worthwhile?
Yes, we do have some of those in place at our critical um, substations. So dual differential, current differential bus protection. Um, Again, you just have to make sure that the circuit breakers have adequate CTs on them, and yeah, you can make that work. And we do have that again for our critical stations.
Okay. A question on IEEE 2800. I think you're trying to remember the number of the transmission related IBR standard, the IEEE 2800. Do you see IEEE 2800 standard helping in keeping conventional protection schemes like distance and directional relays?
Yes, as those standards evolve, and we've um, been following 2800, our transmission planning people have been involved in that. So uh, it does look like it will help, again, in terms of keeping voltage and frequency up, giving the protection systems more time. Yes, it should be helping us.
Okay. There's some questions that are jumping around here, but let me take these two questions together from Rich. Again, one's a statement and then a question. I assume that CCT getting shorter is due to less rotating machines on the system, thus less synchronizing torque. Is that correct? And then followed up with a question. If so, any thoughts on just going 100% IBR and eliminating the CCT stability issue?
Oh, interesting question. Yes, to the first part there. Having less synchronous machines is causing some of those CCT issues. Critical clearing times are getting shorter for stability. Um, if you have a 100% IBR system, do you still have stability issues? That is a good question. Um, but how do you get from here to there? I guess that's sort of the part we really haven't figured out yet.
Okay. And we're getting up towards the top of the hour. I'll take one more question here. I think you touched on this a little earlier, but why does current directionality change with IBRs?
So the non-grid forming resources, grid following essentially, right? Because there was no requirement in the performance standards, I think, it was just whatever the manufacturers put in there. So that impacted the directionality. There was no requirement to maintain things like negative sequence current. And so, that impacts the directionality. We're slowly learning from that. And so having like negative sequence current requirements during faults addresses some of that. I think for the smaller inverter system, the non-grid forming type systems, it depended on the implementation of the voltage tracking from the manufacturer. We see a lot of the older systems where there's just a phase lock loop for voltage tracking. It doesn't get sufficient information, so you don't know what the inverter is going to do. It's all these control loops and control loops and control loops, and sometimes what pops out under fault conditions, is very very rapidly changing, and so it fools the directionality in the relay sometimes.
Another situation of live and learn.
Yeah.
Okay, so we're just a little past the top of the hour, so we're going to need to wrap it up. I want to thank Steve for this very timely webinar and for great insights into the future of protection systems. And as I mentioned earlier, an email will go out once the video file has been posted, and we'll answer the questions we didn't get to and get them posted as quickly as possible. We appreciate your engagement and look forward to seeing you again soon. We have another webinar coming up next week on AirGrid's look-ahead security assessment capabilities in the control room on another high IBR system, followed by our fall workshop at the end of October. Further information on all of the webinars and meetings can be found on our website at esig.energy under events and in our newsletters and informational emails, and you're all invited to attend. So Steve, thank you once again for this very timely and informative webinar, and thank all of you for your interest. We will look forward to seeing you again in the near future. And in the meantime, everyone, take care, stay safe, and thanks for your participation. See you soon.